In this video, we will discuss SN2 reactions. Now, keep in mind that if you find that these videos move too slowly, you could simply try the problems in the problems document. Check your answers against the answers document, and if you need to, skip to particular parts of the videos that cover the problems that are giving you difficulty. Notice that there are links to those documents in the video description box. Also, in the video description box is a table of contents for the video series, and there's a table of contents for each video in the progress bar at the bottom of the video. Now, SN2 reactions are often one of the first reactions that students study in their Ochem class, and therefore, in this first video in the series, we will cover fundamental concepts and techniques for understanding Ochem reactions in general. Then, starting with the second video, the next video in this series, we will begin showing how to use those fundamental concepts and techniques to understand the specifics for SN2 reactions. Let's begin working on those Ochem fundamentals. Let me ask you a question. What do you think is the most important factor in organic chemistry? Now, that's kind of a vague question, so I'll just tell you what my answer is. The most important factor in organic chemistry is formal charges. The most important factor in organic chemistry is formal charges. We'll illustrate why in these videos. Next question. What is the most important tool for predicting what will happen in a reaction? Well, I hope you answered the formal charges. And again, we will show how to use formal charges to predict what will happen in a reaction. Next question. When you draw the products of a mechanism step, what is the most important part of the products to get right? By the way, you can see that in this video series, I will be asking you a lot of questions. And I hope that every time I ask a question, I hope that you'll pause the video and actually come up with your own answer before proceeding with the video. Answer to this question. The most important part of the products to get right is the formal charges. And again, we will be showing why that's so important. Next question. Does nature like or dislike charges? I hope you came up with an answer to that. The answer is nature dislikes charges. Of course, nature isn't really a person, but oftentimes in science, it's helpful to personify nature and pretend that nature acts like a person to give us a better intuition. So we'll get a better intuition for Ochem if we kind of pretend that nature is like a person who dislikes formal charges. We will use this idea to predict what will happen in a reaction. If there's a formal charge, what will happen in the reaction is that nature will try to get rid of that charge. If there's a formal charge on a particular atom, nature will usually try to get rid of the formal charge on that particular atom. Next question. Does nature prefer atoms to be charged or neutral? Well, that should have been an easy one. Again, nature dislikes charges, so nature prefers atoms to be neutral. Nature prefers atoms to be neutral. So again, if you see an atom with a formal charge, you can predict that very likely a reaction will take place to change that atom from charged to neutral. Next question. Does nature prefer charges to be big or small? Answer. Nature prefers charges to be small because a smaller charge is closer to neutral. So again, if you see a formal charge on an atom, you can predict that what will happen in the reaction is that nature will try to reduce that formal charge down to neutral. It will almost never happen that the formal charge will get bigger on a particular atom. Nature almost never wants the formal charge on a particular atom to get bigger. Instead, nature wants to reduce the formal charge to be smaller, preferably to be neutral. Next question. Which atoms are most likely to participate in a reaction? Here's the answer. Usually, the atoms with formal charges are most likely to participate in a reaction. And again, that should make sense to you. The atoms with the formal charges are unhappy, so to speak. They want to get rid of their charges, and they can get rid of their charges by participating in the reaction. So you should focus especially on the atoms with formal charges when you're trying to figure out which atoms will participate in a reaction. There are some exceptions to this pattern, but this is the usual pattern. Now, when you are predicting what will happen in a reaction, that means that you are predicting the mechanism for that reaction. And I hope you already know that you show the mechanism for a reaction by drawing curved arrows. The mechanism for the reaction is represented by drawing curved arrows, which are also called electron-pushing arrows. So now we need to discuss how we can use formal charges to correctly draw the electron-pushing arrows. Let's discuss how to draw those electron-pushing arrows. Now, these arrows show the movement of what? Obviously, these arrows show the movement of electrons. That's why they're called electron-pushing arrows. What's the most important thing to understand about an electron? Its formal charge. What is the formal charge on an electron? Well, I hope that you know that electrons have a negative formal charge. Electrons are negative. So these arrows show the movement of negative electrons from here to here. So, what type of atom should we put at the beginning of this chain of arrows? What type of atom should we put at the beginning of this series of arrows? A negative atom or a positive atom? Pause the video and figure that out. Who goes at the beginning of the series of electron-pushing arrows? A negative or a positive atom? I hope you actually came up with an answer to that. Well, the answer is that we should put a negative atom at the beginning of the series of arrows. Do you see why? Remember that if something is negative, it would like to get back to neutral. And the way it can get back to neutral is by donating its negative electrons. So a negative atom would like to go at the beginning of this series of arrows so that its negative electrons will move away from it and help it get back to neutral. Put a negative atom at the beginning of the series of arrows. Now, that's not always possible. Sometimes there are no atoms with negative formal charges. So who else could we put at the beginning of the series of arrows? Well, sometimes we also have to put sometimes a neutral atom at the beginning of the series of arrows. You should put, if possible, you should put a negative atom at the beginning of the arrows. But if necessary, you can put a neutral atom at the beginning of the arrows. But I hope you can see that we should almost never put a positive atom at the beginning of the arrows. We would almost never put a positive atom, an atom with a positive formal charge, at the beginning of the arrows. Because if something has a positive formal charge and then electrons move away from it, it would become even more positive, right? If you start positive and then negative electrons move away from you, you would become even more positive, less negative, even more positive. But remember, nature doesn't want to make this positive charge bigger. It wants to make the positive charge smaller. So you would almost never put a positive at the beginning of the series of arrows. Well then, what type of atom should we put at the end of the series of electron-pushing arrows? I hope you came up with an answer to that. Well, it should be clear that we get the opposite answer here. At the end of the series of arrows, we want to put an atom with a positive formal charge. If something has a positive charge, it would like to get back to neutral. And the way to do that is to receive negative electrons. By receiving negative electrons, this positive atom could get back to neutral. Now, sometimes there is no acceptable positive atom to put at the end of the series of arrows. When there's no acceptable positive atom to put at the end of the series, we have to put a neutral atom here. But I hope it's clear that we would almost never put an atom with a negative formal charge at the end of the series of arrows. Do you see why? If we put an atom with a negative formal charge here, then when it gained electrons from these arrows, it would become even more negative. But nature doesn't want to make a negative atom more negative. It wants to get it back to neutral. So now we can start to see how we really can use the formal charges to predict how we should draw our electron-pushing arrows. What about for this atom in the middle? What type of atom would we put in the middle of the series of arrows? Almost always we would put an atom with a neutral formal charge. Zero formal charge. Generally, we put an atom with zero formal charge in the middle of the series of arrows. There are some rare exceptions to these rules. In particular, there are some rare exceptions to this rule, but you can learn about those later if they come up later in your course. These rules will work in the vast majority of cases. So I promised earlier that the most important tool for drawing the mechanism for a reaction is the formal charges. And now we can start to see how we use that tool. We use the formal charges to find a good candidate to go at the beginning of the series of arrows and at the end of the series of arrows. And now you can see why the most important thing to get right when you draw products of a step is the formal charges. You have to draw the formal charges for the products of one step correctly because you're going to use those formal charges to figure out what happens in the next mechanism step. By the way, one thing that's a little confusing in Ochem is that there's two different, well, at least two different, there's two different or more than two different systems for assigning charges. What we've been talking about here are formal charges. We've been talking here about formal charges. Later on, we'll learn about a different type of charges called delta charges. There's a different type of charges called delta charges. I just want to mention right now that so far, we're not talking about delta charges. So I'm not saying that you should always put something, so this framework is about formal charges. You should not be trying to apply this directly to delta charges. We'll talk more about how we can use delta charges later in these videos. Now, if an atom is going to participate in a reaction, you want to predict what role it will play in the reaction. What would be an example of a role that an atom can play in a reaction? Well, one example of a role is what's called a nucleophile. And that's a term that I hope that you've already encountered in your class. Nucleophile is one of the roles that atoms can play in reactions. Can you think of any other roles that atoms can play in reactions? Well, I hope you thought of the term electrophile. Can you think of any other roles that atoms can play in reactions? Well, did you think of the term leaving group? That's another term you should have encountered in your class. A leaving group is another role that an atom can play in reactions. Now, there are other roles as well that atoms can play in reactions, but we don't need to get into those right now. For right now, we can focus on these three key roles that atoms can play in reactions. This is really fundamental material for your class, so you really need to know the definitions of each of these roles. How would you define the term nucleophile? Do nucleophiles donate or receive electrons? I hope you said that nucleophiles donate electrons. But we need a two-part definition. It's better to say that a nucleophile donates electrons to join an electrophile. A nucleophile donates electrons to join an electrophile. How would you define the term electrophile? Well, we can adapt this definition. I hope you said that an electrophile receives electrons. But remember, we want to use a two-part definition. It receives electrons to join a nucleophile. An electrophile receives electrons to join a nucleophile. Compare that definition to the definition for a nucleophile. Why is the term electrophile appropriate for this role? Well, do you know what the suffix phile means? Phile is a suffix that comes from, I think, Greek. I think phile is Greek for liker or lover. For example, a philanthropist is somebody who gives a lot of money to charity, perhaps because they are a lover of mankind. A philosopher, the term philosopher comes from the root of lover of wisdom. So what does electrophile mean? Electrophile means a molecule that likes or loves electrons, an electron lover. Well, do you see why it makes sense that this role would go with an electrophile? Because the electrophile likes electrons, it wants to receive more electrons. I think that makes sense. An electrophile is something that likes electrons, and therefore it wants to receive more electrons. So if you remember that phile means liker, if you ever forget what electrophile means, you should be able to figure it out. Phile means liker, electrophile means liker or lover of electrons. It makes sense that something that loves electrons would want to receive more electrons. Now, it's not as easy to see where this term nucleophile comes from, but we can understand the nucleophile term if we focus on the charges. Keep in mind that what's the charge on an electron? You should know that an electron has a negative charge. So when we say that an electrophile likes electrons, another way to put it is that it likes or loves negative charges. We could say that an electrophile, an electron lover, is also a negative lover. It wants to react with things that are negative because it can receive the electrons from things that are negative. Clearly, a nucleophile is the opposite of an electrophile. So a nucleophile must be a positive lover. And that is consistent with this definition. A nucleophile wants to react with molecules that are positive because because it's easy to donate negative electrons to things that are positive. A nucleophile wants to react with things that are positive because it's easy to donate negative electrons to things that are positive. Well, now we can see where this term comes from. It comes from the fact that the atomic nucleus has a positive charge. You've learned in your other courses that an atomic, just like the electrons have a negative charge, an atomic nucleus has a positive charge. So when we say that this molecule is a nucleus lover, what we really mean is that it's a positive lover. It likes to react with things that are positive because those are the things that it's easy to donate negative electrons to. So when you see the term nucleophile, you should translate that as positive lover, and that might help you to remember what the definition of a nucleophile is. Maybe an easier way to approach it is, though, I think it's pretty easy to remember the definition of an electrophile. Since electrophile means electron lover, it's easy to remember that electrophiles want to receive electrons, and then you can just remember that a nucleophile is the opposite. So if you have trouble remembering what a nucleophile is, just remind yourself that an electrophile is an electron lover that wants to receive electrons, and that a nucleophile must be the opposite, which means that a nucleophile wants to donate electrons. And now, how would you define the term leaving group? Students are less likely to know how to define a leaving group. Do you know, do leaving groups donate or receive electrons? Well, leaving groups receive electrons. But remember, we want a two-part definition. We can't just say that a leaving group receives electrons, because then we wouldn't be distinguishing between a leaving group and an electrophile. So we need a second part of the definition to show how a leaving group is different from an electrophile. Well, we could say that a leaving group receives electrons to leave an atom. That's why they're called leaving groups, because they're leaving an atom behind. Now you can see, how is a leaving group similar to an electrophile? They're similar because they both receive electrons. How is a leaving group different from an electrophile? They're different because an electrophile joins something else, whereas a leaving group is leaving something else. Now you can see why it's helpful to have a two-part definition for each of these roles. By the way, there isn't any special name. There isn't any special name for the thing that the leaving group is leaving, so I'll just say that it's leaving an atom. The atom that it's leaving could be part of a larger molecular structure. And we'll see examples of all of these very soon. Very soon we'll get to examples of these. Now, this material that I have on the page right now is absolutely fundamental to your success in the rest of your organic chemistry class. You need to know these definitions like the back of your hand. So now would be a good time to pause the video and memorize these definitions. I hope you did that. So for review, what are the three roles? What are the three roles that we've learned so far that atoms can play in reactions? Nucleophile, electrophile, and leaving group. And pause the video and define those roles. I hope, again, you came up with these definitions. Now, why is it useful to identify these roles? Well, remember, our goal for most problems is to draw the correct electron-pushing arrows. Well, these roles help you to figure out how to draw the correct electron-pushing arrows. Let's see how that works. Let's talk a little bit more about the structure of an electron-pushing arrow. Every electron-pushing arrow has two parts, a head and a tail. Do you know which part this is? This is the tail of the electron-pushing arrow. Which part is this? This is the head of the electron-pushing arrow. Which part is this? The head. Which part is this? The tail of the electron-pushing arrow. So when you've identified a nucleophile, should you put the nucleophile at the head or the tail of an electron-pushing arrow? I hope you actually came up with an answer to that. Well, the nucleophile should go at the tail of an electron-pushing arrow. We draw a nucleophile at the tail of an electron-pushing arrow because a nucleophile wants to donate electrons. Well, this is the right way to show donation of electrons. By drawing the nucleophile at the tail of this arrow, we showed that the electrons are going to be moving away. The electrons will be moving away from the nucleophile, so the nucleophile will be donating those electrons. It's helpful to identify the nucleophile because then you know to put the nucleophile at the tail of an electron-pushing arrow. Now, this raises the obvious question, who should we put at the head of this electron-pushing arrow? But that should be pretty easy because the full definition of a nucleophile is that a nucleophile donates electrons to join an electrophile. That should make clear that we need to put the electrophile at the head of this electron-pushing arrow. We draw the electrophile at the head of the electron-pushing arrow. Now we can see that the nucleophile is donating electrons to join this electrophile. And notice that this arrow is also consistent with this definition for an electrophile. An electrophile is supposed to receive electrons. Well, it makes sense for the electrophile to go at the head of the electron-pushing arrow. Do you see how this shows that the electrons are moving towards the electrophile so that the electrophile can receive the electrons? Remember that the electron-pushing arrow shows the movement of the electrons. So this electron-pushing arrow shows the movement of electrons from the nucleophile, the electron donor, towards the electrophile, the electron receiver. The electrophile is receiving electrons to join the nucleophile, and this arrow is also consistent with the idea that the electrophile will be joining the nucleophile. So we can see that it's very useful to identify the nucleophile and electrophile in the starting materials because that tells you where to draw the tail of an electron-pushing arrow in your mechanism and where to draw the head of that same electron-pushing arrow. By the way, I've noticed that students often confuse the term nucleophile and electrophile, maybe because they both end in phile, because these words kind of rhyme. Oftentimes students say nucleophile when they mean electrophile, or they say electrophile when they mean nucleophile, but you can see that's a very bad habit because we're treating the nucleophile and the electrophile quite differently. So don't confuse the nucleophile and the electrophile. If you confuse the nucleophile and the electrophile, obviously you're going to draw your electron-pushing arrow in the wrong direction. So the word nucleophile and electrophile both end with the syllable phile. But don't let that fool you into thinking that those two words mean the same thing. They mean more like opposite things. So be careful not to confuse the nucleophile with the electrophile. That way you can draw the correct electron-pushing arrow. Now, what about a leaving group? Should we draw a leaving group at the head or the tail of a electron-pushing arrow? Well, remember that a leaving group receives electrons. In order for the leaving group to receive electrons, the leaving group must also go at the head of a electron-pushing arrow. And this is the way the arrow would look. This is, remember that this leaving group has to be leaving some other atom. So here's the atom that the leaving group is leaving. This electron-pushing arrow shows that we're going to break the bond between the leaving group and the atom that the leaving group is leaving. So this is a good electron-pushing arrow because it shows that we're going to break the bond between the leaving group and the atom that the leaving group is leaving. And it shows that while it's leaving, the leaving group will be receiving the electrons from that bond. So this stands for the atom that the leaving group is leaving. Keep in mind that this atom could certainly be connected to other atoms in a larger molecular structure. The atom that the leaving group leaves could certainly and usually will be connected to a bunch of other atoms in a larger molecular structure. I'm just using the word atom here to make clear that we should think of the leaving group as leaving one particular atom that very likely will be connected to a bunch of other atoms in a larger molecular structure. Again, all these ideas will become clearer very soon when we start applying these ideas to specific examples. It's crucial to identify the roles that atoms in the starting materials will be playing in the reaction, because once you have identified those roles, now you know where to draw the heads and tails of your electron-pushing arrows. You should draw a electron-pushing arrow pointing from the nucleophile towards the electrophile. And we also draw a electron-pushing arrow that looks like this from a bond pointing towards the leaving group. Now, how can you predict what roles an atom will play and which atoms will play which roles? What is our most important tool for predicting what roles the atoms will play? I hope your answer was formal charges. How can we use the formal charges to predict the roles? Well, suppose an atom has a negative formal charge. If an atom has a negative formal charge, what roles would it be likely to play? I hope you answered nucleophile. If something has a negative formal charge, it would like to get back to neutral. Well, remember, electrons have a negative charge. Electrons have a negative charge. So if something starts with a negative charge, the way to get back to neutral is by donating its negative electrons. If an atom has a negative formal charge, it's likely to play the role of nucleophile so that it can donate its electrons. Remember, we learned earlier that we like to put negative charges at the beginning of the series of arrows. By the way, later you will learn that there's another important role that an atom with a negative charge can play besides nucleophile, but we don't have to get into that right now. And later you will learn other clues for when things can be nucleophiles besides a negative formal charge. But this is a good clue for us to focus on right now. What about if an atom has a positive formal charge? Well, it should make sense that atoms with positive formal charges are candidates for being electrophiles or leaving groups. But I'm actually not going to get into that right now because for the SN2 reactions that we're going to be working on, this turns out not to be too important. For the SN2 reactions that we're going to be working on, there will rarely be an atom with a positive formal charge that is a good candidate for participating in the reaction. So I won't actually focus on positive formal charges right now. Now, if we're not going to use positive formal charges to identify the electrophile and leaving group, we need other clues for who's going to be the electrophile and leaving group. Well, for the SN2 reactions that we're going to be focusing on, the main clue for the electrophilic atom will be a delta positive charge. Remember that I mentioned earlier that there's two different systems for assigning charges. There's the formal charge system, and you can also assign delta charges. Well, the clue that we'll be focusing on for electrophiles is an atom with a delta positive charge is likely to be a good electrophile. This clue should make sense to you. This clue is consistent with the definition of an electrophile. It should make sense that something with a positive charge would want to receive negative electrons. Unlike charges attract. When something has a type of positive charge, it's attracted to and wants to receive negative electrons. And later in the videos, we'll discuss how to identify when something has a delta positive charge. What about for the leaving group? What clue will we use to identify the leaving group? Well, it turns out that the helpful clue is just to memorize that neutral chlorine, bromine, and iodide are good leaving groups. We should just memorize that neutral chlorine, bromine, and iodide are good leaving groups. By the way, here I mean neutral, zero formal charge. These would be chlorine, bromine, and iodide with zero formal charge. I'm not talking about delta charges here. Generally, you should assume that I'm talking about formal charges, unless I specifically mention that I'm focusing on delta charges. So these would be chlorine, bromine, and iodine with zero formal charge. Why are these atoms good leaving groups? Well, for simplicity, I'm not going to get into that right now, although you might find an explanation for that in your textbook. Let's just memorize for now that neutral chlorine, bromine, and iodide are good leaving groups. Do you know where chlorine, bromine, and iodine are in the periodic table? Here's chlorine, bromine, and iodide in your periodic table. You can see these are all from the seventh main column, which is called the column for the halogens. On the other hand, notice that neutral fluorine is not considered a good leaving group. Neutral chlorine, bromine, and iodide are good leaving groups. Neutral fluorine is not a good leaving group. Perhaps in a later video series, we can explain why fluorine is not as good of a leaving group as chlorine, bromine, and iodide. Again, keep in mind that right now we're just focusing on the clues that are particularly helpful as we start working on SN2 reactions. As you proceed with your Ochem class, you'll have to learn more clues later. You'll learn other clues that you can use to predict the roles that atoms will play. These are the clues that are helpful for right now. Now, the material that we have on the screen right now is absolutely fundamental, not just for SN2 reactions, but for the entire remainder of your organic chemistry class. So I encourage you now to pause the video and, first of all, make sure that you have all of this material clearly in your notes. And also, make sure that you've actually memorized this material. Now is a good time to pause the video and make sure you've actually memorized this material. I hope you actually did that. So we can do a short quiz. Can you name the 3 roles that we've just talked about? Can you give the exact definitions of those 3 roles? For each role, can you show whether that role should go at the head or the tail of an electron-pushing arrow? And can you identify the clues that we've talked about for identifying which atoms will play which roles? You might want to try to write down the answers to all those questions on a blank piece of paper. And here's the answers that you can check. In order to succeed in your organic chemistry class, you need to know all this material on the screen like the back of your hand. So you'll need to keep working on that. Now let's try some exercises to practice those fundamental skills we just went over. So here's a bunch of molecular species, and for each of these we need to predict the roles that the atoms are likely to play. So please pause the video and try to identify the roles that atoms in each of these species will play. Try to be specific about exactly which atoms will play which roles. I hope you actually gave that a shot. Well, notice that this iodide has a negative charge, and we know negative charges tend to make atoms into nucleophiles. This atom wants to donate electrons to get rid of its negative charge. So we would expect this iodide to be a nucleophile. A negative charge makes an atom nucleophilic, so it can donate its electrons to get rid of the negative charge. For the same reason, we would expect this bromide to be a nucleophile because of the negative charge. Again, we would expect that this negative charge makes this species nucleophilic, but be specific about which atom will play the role. Is the carbon the nucleophile, or is the nitrogen the nucleophile? Well, notice that the negative charge was drawn next to the carbon, not next to the nitrogen. That indicates that the negative charge is on the carbon, not on the nitrogen, and that indicates that the carbon will be the nucleophile, not the nitrogen. So we would expect the carbon here to play the role of nucleophile. That's what I meant about being specific about which atom will play the roles. Here again we see a negative charge, but which atom will, that would indicate a nucleophile, but which atom will be nucleophilic? One of the carbons, one of the hydrogens, or the oxygen? Well, the negative charge is on the oxygen, so we would expect the oxygen to be nucleophilic. Again, in this case, the negative charge is on the sulfur, so we would expect the sulfur to be nucleophilic, not the carbon or the hydrogen. By the way, I'm not saying that these are the only roles that these atoms could play. Later in the course, you'll learn another important role that some of these could play. But for now, one role that we would predict these might play is nucleophile because of the negative charges. Here's some more practice problems. Please pause the video and again try to identify the roles that atoms in these molecules will play. Try to be specific about which atoms will play which roles. Gave that a shot. Well, first of all, notice that, for example, in this molecule we see a neutral iodide. Here we see a neutral iodide. So we do not expect this to be a nucleophile. Instead, we've learned that a neutral iodide is a good leaving group. So we would expect this neutral iodide to play the role of leaving group. This is a great illustration of how crucial formal charges are in organic chemistry. This iodide is a nucleophile, but this iodide is a leaving group. How can you tell the difference? From the formal charge. If you see a negative iodide, that's likely to be a nucleophile. But if you see a neutral iodide, that's likely to be a leaving group. Now we can go beyond that, though. We could also say that this carbon has a delta positive. Iodide is to the right of carbon in the periodic table. Iodide is slightly more electronegative than carbon, and as a result, we would expect this carbon to have a delta positive charge. And we know that a delta positive charge is a sign of an electrophile. Delta positive means an electrophile. So we can say that this carbon would be expected to be an electrophilic carbon. To repeat that logic, iodide, you should know that iodide is to the right of carbon in the periodic table. That means that iodide is slightly more electronegative than carbon. That means that the iodide wants electrons more. The iodide wants electrons more than the carbon does. Here is iodide in our periodic table, and here is carbon. Because iodide is to the right of carbon in the periodic table, that indicates that iodide is likely to want electrons more than the carbon does. Since the iodide wants electrons more than the carbon, the iodide is going to be pulling the electrons in this bond closer to itself. The iodide will pull the electrons in the bond closer to itself than to the carbon, but remember the electrons have a negative charge. So if we pull these negative electrons towards the iodide, that will make the iodide a little bit partially negative and the carbon partially positive. We don't really care much about this delta negative, so I'll erase it now. But the delta positive charge is the clue that this carbon will be electrophilic. Now, to tell you the truth, iodide is really only a little bit more electronegative than carbon. This would be a pretty small delta positive. But anyway, this method gives us the right answer. This method gives us the right answer that this carbon will be electrophilic, so we'll use that method to predict here and explain why this carbon is electrophilic. Notice that this carbon is not particularly electrophilic. In fact, we don't really expect this carbon to participate in the reaction. There's no particular reason to expect this carbon to participate in the reaction because this carbon is not attached to anything that's going to give it a delta charge. It is not attached to anything that's substantially more or less electronegative than itself. So again, this is what I mean by being specific about which atoms will play which roles. Be specific about which carbon will be the electrophilic carbon. It's this carbon in this case. To be more specific, we could say carbon 2 here will be electrophilic. Now let's try to apply that to these molecules. You might want to pause the video and try these examples again if in light of what we just learned from this example. Well, here we have a neutral bromine. Neutral bromine is likely to be a leaving group. Negative bromine is nucleophilic. Neutral bromine is a leaving group. Also, bromine is to the right of carbon in the periodic table, so the bromine wants electrons more than the carbon does. Here is bromine in our periodic table, and here is carbon. Bromine is to the right of carbon in the periodic table, which indicates that bromine wants electrons more than carbon does. Neutral bromine wants electrons more than the neutral carbon does. So the bromine is going to pull the electrons in the bond closer to itself, which would tend to leave this carbon with a delta positive charge. And a delta positive is an indication of an electrophile. So we expect that this carbon will be electrophilic. So be specific, I guess I'll give these different numbers. Be specific, we would expect carbon 4 here to be electrophilic. And we would expect carbon 3 and 5 to be unreactive. And we can try that same process over here. Here we see a neutral chlorine. Neutral chlorine is likely to be a leaving group. Remember, we haven't explained why a neutral iodide or bromine or chlorine is a good leaving group. We're just memorizing that for the time being, although you might find an explanation in your textbook or your lecture notes. Now, chlorine is to the right of carbon in the periodic table. Chlorine wants electrons more than the carbon does, so the chlorine will pull the electrons in the bond closer to itself. Therefore, that would tend to leave a delta positive charge on this carbon, which would tend to make this carbon electrophilic. Now let's be specific. Be specific, we should say carbon 6 will be electrophilic, because that's the carbon with the delta positive charge. Carbon 7, 8, 9, 10, and 11 will be unreactive, because they don't have any particular delta charge, because they're not attached to anything that's substantially different than them in electronegativity. Taking my time and talking through the logic slowly for all of these examples, but you need to practice these skills till you get to the point where you can quickly identify the roles that are likely to be played by specific atoms in your starting materials. This is a fundamental skill for your Ochem class. Now let's introduce another important term that we need to understand for understanding SN2 reactions. We're going to be using the term alpha carbon. And in these videos, we're going to use the term alpha carbon to refer just to the carbon that is attached to the leaving group. The alpha carbon is the carbon that's attached to the leaving group. That's just going to be a useful term for us in learning about SN2 reactions. There are other types of alpha carbons that you might learn about later in your course, but for this material, this is the useful definition of an alpha carbon. So let's try labeling the alpha carbons that we have here so far. What's the alpha carbon in this molecule? The alpha carbon in this molecule is carbon 2, because carbon 2 is attached to the leaving group. Carbon 1 is not the alpha carbon. Who's the alpha carbon here? The alpha carbon in this molecule is carbon 4, because carbon 4 is attached to the leaving group. Carbons 3 and 5 are not alpha carbons. In this molecule, carbon 6 is the alpha carbon, because carbon 6 is attached to the chlorine, which is the leaving group. Carbons 7, 8, 9, 10, and 11 are not alpha carbons. So also that tells us, is this an alpha carbon? Well, we are not going to call this an alpha carbon because it's not attached to a leaving group. We won't call this an alpha carbon. Is this an alpha carbon? We will not be calling this an alpha carbon because this is not attached to a leaving group. So that's the useful definition of the term alpha carbon for this topic. For the topic we're working on now, it's useful to think of the alpha carbon as the carbon that's attached to the leaving group. So this is not an alpha carbon because it's not attached to a leaving group. This is not an alpha carbon because it's not attached to a leaving group. So notice many molecules don't have an alpha carbon as we're using the term here. These molecules, these species, don't have any alpha carbons because there's no leaving groups in these species. That's the useful way to use the term alpha carbon when you're studying SN2 and SN1 reactions. So for purposes of studying this material, we will use the term alpha carbon to refer to a carbon that's attached to the leaving group. We will soon see why that's a useful term to be using for SN2 reactions. All right, now we've completed our review of some Ochem fundamentals that should help you with organic chemistry reactions in general. And you can now proceed to the second video in the series, where we will start applying those Ochem fundamentals to understand the specifics of SN2 reactions. Did you find this video to be helpful? If so, you can support the videos by making a monthly pledge of $1 or more at my Patreon page. You can visit my Patreon page by clicking the link on the screen or by using the link in the video description box. Thank you.